Chapter 18 on thermodynamics and equilibrium. So thermodynamics is a branch of chemistry that studies the relationship between heat and energy in a chemical reaction or a chemical or physical change. So far in Chapter 6, we talked about one property, enthalpy, which was the heat for a given reaction, or in general, heat for a given reaction at constant temperature. Constant pressure, sorry. So heat, remember, was the symbol Q. So at constant pressure, we do a little p to denote the fact that we're at constant pressure. So enthalpy was equal to Q at constant pressure. So there are three laws of thermodynamics that govern how this relationship works between heat and energy and a physical change or a chemical change. So the first one is the law of conservation of energy. The second one is talking about entropy in relationship to a spontaneous process. And then the third one has a way to quantify entropy for a given substance. So we're going to go through each of these one at a time into more detail. So the first law says the internal energy for a given substance is always conserved for any physical or chemical process. So internal energy has the symbol U, and it's the sum of all the energies that make up that system. So the system is typically talking about the reaction or your substance or whatever it is that you're measuring. The surroundings would be everything else around it. In general, there are two basic types of energies that we're going to add up. The kinetic energy, which is the energy associated with motion. So in our chemical reaction, that would be of molecules, electrons, ions, particles, whatever your substances are. Potential energy is the stored energy that it has. In a chemical process, this energy is stored in the bonds. So the bonds that hold atoms together or molecules together, things like that. So energy can't be gained or lost in general. It can only be transferred between the system, which is our reaction, and the surroundings, which is everything else. We can measure how much it changes for any system that undergoes a change. So during any change, we can measure how much it changes. Rather than actually trying to measure what the numbers are at the start and the beginning, we just measure the change. So we measure the delta U. If the change is a positive number, then that means the final energy is higher than it was at the initial. So that means the system has gained energy from the surroundings. So then therefore the surroundings have lost. If it's negative, that means the initial is higher than the final, so it has lost energy. So the surroundings have then gained. So we have this sort of give and take relationship between the system and the surroundings of this energy transfer. So we're going to talk about two basic types of energy transfer. So the first one is heat, which is Q. And this is energy associated with a temperature change. So if the two substances, your system and surroundings, have a different temperature, one is hotter and one is colder, then there's going to be a transfer until they are both the same temperature, from the hot to the cold. If heat is released by the system, then heat, or Q, for example, is a negative number. That's also an exothermic reaction. If heat is absorbed by the system, so from the surroundings it absorbs it into it, it's a positive number. This would be considered an endothermic reaction. The other type of energy transfer is work. So work has a symbol W. So this is an energy transfer that results when a force pushes an object through some distance. So your formula is force times distance for that given system. In chemistry and chemical reactions, we typically observe this force as a pressure, and the distance is observed through how much the volume of a container changes, whether it gets increase or decrease. So work can also be pressure times change in volume. Now, the notation of the signs is a little confusing. So we want to denote work done by the system is a negative value, and work done on the system, no, I flip-flopped these. Oops, so sorry. On the system is negative. They are opposite from your Q's. Yeah, okay. So for example, if you have this reaction, zinc and hydrochloric acid, this reaction is exothermic. It releases heat out. It also forms hydrogen gas. When that gas is formed, it's going to push the container from one volume to another volume. That is a type of work. So you can actually measure that by how much pressure it had to begin with, and then also how much the volume of the container changes. So the change in internal energy, so our delta U for any chemical reaction, can be calculated by summing up the total amount of transfer by your two different types, so your heat and your work. Okay. When a chemical reaction occurs, we know your energy is going to change because the kinetic energy and potential energies are going to change as your reactants turn into products. So let's say we have this reaction. 1 mole of zinc and 1 mole of hydrochloric acid. You're going to form hydrogen gas. The heat of this reaction has already been tabulated, 153.9 kilojoules of heat. What we also need to figure out is how much work this system does, because we form a gas. So we know what the pressure is, and we know the volume. Now, if we do our formula for work, what we need is the units of work to match the units of heat, so that way they're all in the same unit for energy, which has to be some sort of joule. So Q is already in kilojoules, so we want W to end up being in kilojoules. So the only way to get a pressure times a volume to equal joules is to have pascals for your pressure and cubic meters for your volume. So that's why we had to change them from one units to another. So then we can just multiply negative pressure times our volume and we get 2474.5 pascals times cubic meters is joules. So this is 2.47 kilojoules. Negative because we had a negative sign for work. So then the total amount of energy change is the amount from the heat plus the amount from the work. So notice that the majority of the energy change is due to the heat being released. That's the most amount of energy that's being transferred is through heat. But there is a small amount that is transferred through that work process of pushing the volume out away as that gas is being produced. So now we can more precisely define enthalpy. So if we said U was equal to Q plus work, We know Q is equal to my enthalpy, and work is equal to negative pressure times volume. So we end up with U is equal to H minus P delta V. So if we solve for H, U plus. So now we have a more exact definition of enthalpy. It's the internal energy plus the pressure times change in volume. Now, if your system does very little work, meaning the delta V is almost zero, then H is equal to almost just the internal energy. And in this case, that's going to be equal to pretty much just Q if we do very little work. So that's why we can make that assumption that H is equal to Q, because for the most part, it is going to be a good enough assumption. So, at a given temperature and pressure, a substance has a definite enthalpy, and we call those enthalpies of formation. So how much heat or energy it would take to form that substance. And we typically measure what's called the standard enthalpy change, which we denote with a little naught. And that just means that we are forming this substance at 25 degrees Celsius at a pressure of 1 atm, and we're trying to make 1 mole of it. So for most substances, we can tabulate that. There are charts in your book for each most common substance to form any substance. We can use this to figure out the enthalpy for an entire reaction using a summation law. So this was your summation law in green. So the little e, these are sigmas. This means sum of the formation for your products minus the formation of your reactants times the N and the M are your coefficients. So if you have to form more than one, you have to double the amount of heat. If overall the delta H is positive, that means overall it's endothermic. Negative means exo. When we calculate the enthalpy for a whole reaction, we do Rxn. So it's changed for a reaction. So, for example, ammonium and carbon dioxide form urea and water. So the enthalpies of formation have been given to us. If they weren't given to you, you could look them up. So the first part of the summation law is to calculate each of them by their coefficient. So this one we would have to multiply by 2 since we have 2 ammonias. And then we sum the totals on the reactant side and the products. And then the enthalpy of your reaction is going to be your products minus your reactants. So overall, this reaction is exothermic. All right, I'm going to stop here, and we're going to make a part 2 video that has the second law and third law.